Homework 7, I moved it, right, to Thursday. Somebody wanted an extension. It's moved to 25th. I have one more homework which I'll post, which is based on this. Okay, let's. Okay, so today's class is going to be integral control as well as doing simulating a real system, which is a pendulum. And so I'm going to share this code with you, but essentially go through the README that basically tells you the information, otherwise it'll be hard for you to follow. So basically the problem where the pendulum starts from 0 position, which is along the x-axis like this, and we want the pendulum to spring up pi by 2. So run the file. This is the main file. And then you'll see the animation and plot. Essentially what I'm trying to do is I'm doing a PD control. So the name of the folder, which would make it obvious, is called naive PD control. So here, pendulum naive PD. Let's see what happens. I'm going to take the main file. Drop it there. And essentially it's the same equation which we derived for we did the dynamics of a single link pendulum some time back. We wrote the Lagrangian and so on. It's the same file, except that now there's control. Specifically what we do is there are 3 things which need to be set. The proportional gain 100, the derivative gain is 0.1 times the proportional gain, so it's 10, and the reference is pi by 2. 0 is this, pi by 2 is upwards. The place where the actual code which does the control goes in would be in the right hand side. Right? The right hand side has a place for the torque. So actually I put it in a file called controls, so that way I can separate out the right hand side from the controls. So let me open that file. So the file called control. Okay, essentially the control is basically telling what the torque should be, and that is basically a PD control, proportional term times the difference between the angle and the reference, and then KD, which is the derivative gain times the velocity. So when we run this, so it's going to do a simulation, then an animation, and then do plots. So from the simulation you can see it overshoots. If you didn't notice it, I'll play it again. You can see it goes from 90 but overshoots and comes back to. Okay, and so that's the animation. Here is the torque, this is the velocity, and this is the position. So starts from 0, we want to go to pi over 2, which is 1.57. You can see there's an overshoot, and then it basically settles to pi by 2. Velocity is an overshoot, and clearly this is because we do not have critical damping in the system. If the system was critically damped, then we wouldn't have this issue. You can try to increase the damping and see what happens. So one way to do this is to just actually guess what the critical damping is. So this looks like it doesn't overshoot. Let's look at the plots. So right here you can see it does not overshoot, but it takes awful lot of time. It takes more than 2 seconds to actually settle down to pi over 2. So that's probably more than what we need. We need less than 0.5, but more than 0.1 times proportional gain. So the way to do this is, instead of guessing, which is hard, we can use what we talked about in the last class on control law partitioning. So this was probably 2 classes back, where I talked about creating a controller which reduces n degree of freedom system to multiple independent first order systems, second order system, but they're independent. Let's see where this is. I believe this was lecture 18, which is last class. Yeah, so this is control partitioning, where essentially I choose the torque to be M, an estimate of mass, KPQ, proportional gain times Q, KD times Q dot, Coriolis term, and the gravity term. If I do this right, then the system reduces to system which looks like this. This is a spring mass damper system where mass is 1, damping is Kd, which you can choose, and the proportional part is Kp, or the spring stiffness is Kp, but you can choose these things. And turns out that to make it critically damped, all you need to do is choose Kd equal to square root Kp. So we can take this idea and now change our code to have critical damping. So I'm going to close this files because I have a new folder which does critical damped. So I call that second control partition. We'll open that. Let's put one link main, and let's open the control because that's where I have the actual control partitioning law. First, let's run this file and see if we get critical damping. If there's an overshoot, so it goes there, comes to stop at pi divided by 2, and then let's look at the plots. Torque, velocity, and position. So you can see position, it goes from 0 to pi by 2. There's no overshoot, and since this is critically damped, this is the shortest time you can get it to pi divided by 2. You can't, well, this is the shortest time for that particular Kp. If you want to make it any faster, so it takes about 1 second to get to pi divided by 2. But if you want it to go faster, then what you need to do is you need to change the Kp. So here I'm not choosing Kd or the damping derivative term because the derivative term is defined as 2 square root Kp. So I only set Kp. So let's change this to 500 and see if that will make it faster than 1 second. So simulate. Stops. Let's go and look at, oh, it's not done yet. It's done now. This is the velocity. Actually, let me run this again. It actually overwrote the figure 1 which had the position. So I need to wait for it to finish, which will be indicated here. Okay, it stopped. Let's close this, close the torque. Look at the velocity, and you can see that the position now gets to pi divided by 2, but a lot faster than 0.5 seconds, less than 0.5 seconds. So you can keep increasing Kp till it gets faster and faster, but beyond some point of time, you'll see that it goes unstable. In the case of simulation, it goes unstable because I used ODE4, which has a certain step time, and if you go any faster, I think it's about 10 raised to 4, it'll go unstable. But in the real system, what will happen is there'll be sensor noise, so the position data will be noisy, and that noise will get multiplied with your gain, and that will lead to instability. So actually in this code, I have means to simulate noise. Okay, I've already set that up here. If you want to introduce noise in the velocity, then you can add, let's say 4. That's too much. Let's do 0.5, and then run this. You can see it's shaking back and forth. That's because your gain is getting multiplied with the noise. And if you look at the data, torque is shaky, velocity is very shaky. Overrode the position, but it's all shaky because there's noise, and so it's actually on the verge of getting unstable because you saw that it was shaking up. If you raise it to 800, I think it'll go unstable. Let's see. So this is introducing noise in the system. So this is simulating an actual system. Close this. This is velocity, and you can see that it tries to track position, but it's noisy. Okay, so so how do you deal with a system which has noise? Well, you could change the sensor to be less noisy. That's one way to do it. But there are other ways in which there's an entire field of controls called estimation, which basically takes data which is noisy and estimates the actual position. It's a lot more smoother. there's something called Kalman Filter, which you might learn if you took a course in controls. There's something called Linear Quadratic Estimator, LQE, which you'll also learn if you take a advanced course in controls. So that's beyond this course, but that's something to remember. So let me get this back. You can play with this. I've put noise and disturbances and so on. There should be a README file which will guide you through what to do. Okay, so that was a real system, a system which has a physical system, a pendulum, okay, which is actually a nice benchmark problem. Okay, next thing I'm going to talk about today is what happens if there's a persistent disturbance and the need for integral control. Okay, so far we've talked about PD control, a proportional derivative control. This is a layer on top of that. Integral control. So let's motivate this. So let's look at this system now. The same simple system which will be used to motivate this example, and then we'll make it a little bit more complicated by looking at the pendulum. So the system is M Q double dot plus CQ dot plus GQ equals torque. So that's the system we've talked about, that torque is something you can control. However, this system has an unknown disturbance. Okay, the number of ways in which this could manifest. You're doing an experiment, it's windy, that's an unknown disturbance on the pendulum. You're doing the experiment and somebody is knocking the pendulum with a torque, that's an unknown disturbance. Sometimes your calibration is incorrect for the torque sensor, that's a disturbance. And when you're designing the system, when you're designing the controller for the system, you do not know about T disturbance. You have no idea. Okay, you still want to create a controller which would achieve whatever you want in the system. In this case, we are doing set point tracking. So this is unknown. Okay, even though I wrote down the equation, it's not known. So what we can do is, even though we don't know about anything about the disturbance, but we can design a control law based on control law partitioning. So we design a controller of this form: torque equals M times, this is, I'm rewriting the control law partitioning control law. Okay, and that is, I do not know anything about the disturbance. I don't even know that there's a disturbance. So let's put 2 in 1. We have MQ double dot plus CQ dot plus GQ. So I'm going to try to now analyze the system when it is subjected to the disturbance, but I do not know the disturbance, so I just put the control law partitioning law in that. So that's my assumption that that will work. So I put it in the equation 1, so I get M minus KPQ minus KDQ dot plus CQ dot plus KQ plus tau disturbance. And so if I move things around, I would get M Q double dot plus K D Q dot plus KPQ So I can cancel this with this. This should be GQ, my bad. So I can cancel the GQ on both sides, and I'm left with this equals tau disturbance. Okay, now what happens is when the system reaches, this should be MQ double dot. Okay, now it's better. Sorry. Should be like this. Okay, so what's going to happen is when I do the simulation of the system and I'm trying to achieve a certain set point, in this case the set point is 0 because in my KP term I have Q, this is Q minus 0, so the set point is 0. When I perturb the system from 0 and let it go and things reach steady state is when velocity is 0, acceleration is 0, right? The rate of change of position and velocity is going to be 0. So steady state, we would have Q dot equals Q double dot equals 0. So I'm setting this up in that equation to get M KPQ equals tau disturbance, and so at steady state I would have Q equals tau disturbance times M times Kp, which is basically now the steady state error. Okay, again I do not know this disturbance. I naively designed the controller assuming that the disturbance is 0, but when you actually simulate the system you'll see that the steady state disturbance Q is not equal to 0. It's tau disturbance divided by M times Kp. So one way of reducing this disturbance to 0 is, well, you cannot control the mass, you can only control Kp. If you make Kp equal to infinity, you get Q equal to 0. But you cannot put Kp equals infinity because in a realistic system there's noise and that's going to affect your set point tracking. So you cannot basically reduce Q to 0. You can make it small by increasing Kp, but at some point you'll be stuck by noise. So this particular controller, which is a PD controller, always has a steady state error if there are disturbances of that nature, constant disturbances. So what we do the way we solve this problem is we add something to the controller, which is known as an integral control. So what we do is change the controller to be like this. Torque equals mass times minus KPQ minus KDQ dot. Okay, so this part is the same. The addition I do is I have a KI integral Q dt, okay, which is the addition, plus CQ dot plus GQ. So what I've done here is added integral term. Okay, now with the integral term, let's put this in the equation. Put in system equation 1. So now we have M times Q double dot plus CQ dot plus GQ equals M times minus KPQ minus KDQ dot minus Ki integral Q dt plus CQ dot plus GQ plus the disturbance torque. Okay, let's move things around. So we have, before I do that, let me get rid of CQ dot, GQ and GQ on either side. So I'm left with M q double dot plus, sorry, this should be in bracket, q double dot plus kpq plus kdq dot plus ki integral q dt equals tau disturbance. So at steady state, okay, before we do that, let's differentiate this expression because I don't like this integral here. So differentiate the expression above once. So I would have m times q triple dot plus kpq dot plus kd q double dot plus ki. Derivative of integral is the value itself, q. So it's q equals torque dot disturbance. Okay. Now look at the steady state. We have q dot equals q double dot equals q triple dot equals the rate of change of disturbance. The disturbance is constant, it's not a function of time, so it's going to be, the derivative is going to be 0. So we're left with m times kiq equals 0, and that means q equals 0, or in other words, this implies no steady state error. Okay, so this is a sort of like a proof which shows that if you have a constant disturbance, then with an integral controller, you will drive the steady state error to 0. And you do not need to know anything about the disturbance except that it's a constant. If you know it's a constant, you put an integral control, it'll kill it off without knowing the actual value of the disturbance. Okay, so how do we implement this? The equations for one way of implementing this in hardware, the way you'll implement this is you'll actually take q, which is the position, and take that position and add it every instant of time. So you generate that sum. It'll actually be a sum. This will be a sum, and you can do it that way. The way to do it with ODE4 or ODE45 is you can actually change your right hand side to include one more variable, which will make it very easy to implement this. Implementation in ODE4 or ODE45. So originally we had this code. So the code which I showed you had two states, Q. So states original RHS had let me do it this way. So again, the equations are mq double dot plus cq dot plus gq equals tau plus tau disturbance. So in the original RHS, this is for the PD controller, the state was q and q dot, and so when you wrote the equation x dot, this is in the right hand side, you wrote q dot for the first one, and for the second one you wrote tau plus tau disturbance minus cq dot minus gq divided by m. So this was the original right hand side for the PD controller. For the PD controller, you just need the position and velocity, which you got. Now we'll modify the RHS to include the new state PID control. So the new state is x equals q dot, and this is the trick. You basically have a third state which is integral q dt. Okay, it is a fictitious state. You just define this so that you can implement this with the PI. You can implement the PID controller. So x dot now is going to be q dot. First term remains same. The second one remains the same. The third one, which is going to be the derivative of q dt, is going to be q. So now you can use this. This is your state, and that will be fed into your integral controller. So if that's not clear, it's going to be clear in the code when I show it to you. Oh, this is first. Let's go through this. The main file. Okay, so this is like a very hypothetical example. Spring mass damper, mass 1, damping 1, k equals 10, and the constant disturbance of 2. What I did here was I have kp, kd is basically determined from the control partitioning. In this case, it is not control partitioning, right? It's basically using that formula for critical damping, which we talked about the first class when I introduced this topic. The integral control is 0. So when I run this, disturb the system, let it go, there's going to be a steady state error, which you can see here. What's my goal? It's to go to 0, but I'm here at 0.15 because of that disturbance. So the way to get to, so I put this into 0.5, let it go. And if there was no disturbance, it would have gone to 0. Because there's a disturbance of 2, right here, it goes to 0.15. So now I can increase the gain. And by the way, you'll forget this. There's a video, but you can also read this, the README, what you're supposed to do. Okay, let's increase the, I don't know, let's put 5. And run this. So you can see it goes to 0 because of the integral control. That's the hypothetical example. Let's do a physical example which has some meaning. PID control of a pendulum. So again, I'm going to open the one link main. You got to go through the README to understand what you need to do with the files. So README is here, right there. So it starts from 0 position along the x-axis. We want it to go up pi by 2. There's a torque disturbance set by disturb T1 mean equals 5. First we set k, the integral control, to 0. Run the file. See what happens. So I need to put this to 0. And then disturbance is 5. And here I've not chosen, you can see that I've not particularly chosen the control partitioning. I just used some PD controller. Okay, so when I do this, I run this. For this system, you will see overshoot because the KD is not tuned by control partitioning. Okay, it's still simulating. Okay, done. This is figure 4. Let's close that. This is the position. You can see that the error. So I'm trying to go to pi by divided by 2. There's an overshoot and there's an error. This is the steady state error which I do not like. And it comes because the torque is not, the disturbance torque is 5. So what I do is I increase the gain. Let's put 10 and see what happens for the integral control. And again, this is not a critical damp system, right? Because the KD was not chosen based on control partitioning. So it's still simulating. Okay, it's done. Let's close this. It's getting a little closer. It's not quite there. I need to increase this further. Let's just make it 50, right? Originally, let's run this.
So you say that this system is not critically damping because KD what?
The KD here, let's just finish. The KD is 0.1 kp. I just put some number there, which is about 10. The actual value is more complicated than that, right? You need to have the control partitioning and you need to find the critical damping. It's not been there, but you can easily program that. I already have code, which I showed you like in the beginning of the class, where I do critical damping for Pendulum, in which case there was no disturbance. So it stopped. Let's see the errors there. See, it's almost 0. It works. So here you can see that the KD is not critical damped. Here, right here. So in this case, what you notice is that there's an overshoot given by that, but it settles down. So if you want both, you want critical damped as well as steady state error, then you want to have the controller based on control partitioning. So you have critical damping. On top of that, you need to put a KI so that the steady state error is 0. So I've not done the control partitioning part here, but you can do it. Okay, so what we are left, so that's it for today. But what we're going to do next time is actually how do you do tracking? So we did trajectory generation, right? We want the pendulum to go from this point to 30 degrees to minus 30 degrees or minus